All right, guys, welcome back. Today, guys, we'll be talking about properties of gases and combined gas law. All right. Actually, we're going to discuss about the other gas laws, but we're going to focus more on the combined gas law. All right. So let's talk about gases, guys. We all know that gases are one of the states of matter, like a solid and liquid. Okay, but gases are unique in such a way that you can't really see them. Unlike liquids and gas. I mean, liquids and solids, you can see them, but gases, not really. All right. So how do we describe gases? Okay. How do we describe gases? Well, we describe gases by looking at their behavior. Right. Now, it's the same thing with asking you, describe to me your, let's say, girlfriend, and you don't have a girlfriend. So what you do is you describe an ideal girlfriend. Okay. Same with gases. When I ask you to describe a gas, most of the time, what you're going to do is use your imagination and describe that gas. And that's called an ideal gas. All right. So ideal gases, guys, are simply imaginary gases, which are, gases without all the complications of stuff. Okay, so they are the simplest, most basic model of gases. All right. So when we describe them, we can actually describe them in just a few behaviors. Right. So first one. Okay, we can think about gases, which are ideal gas. Don't forget, as being very very tiny. So gases are made out of very tiny particles and they are very, very far apart. So this is the main reason why, more or less, you can't see gases. All right. And if you try to karate chop air, your hand just goes through air because the particles are very far apart and your hand just passes through right between them. Unlike if you try to karate chop a table, your hand's going to hit the table, most probably it's going to stop there. Because again, the particles are very, very close in the solid. Okay. They're very, very close in the solid, and therefore your hand basically stops there. Okay? All right. So, guys, imagine that particle. All right. Imagine that particle. So, let's say you're Jesus and you can see the particle, and this is that particle right here. Let's say this is that particle right here. Let's draw a particle right there. All right. This particle is flying. Okay. Let's say this is the wall of our container right here. This is our, let's draw a container wall right here. This is, let's say this is a container right here, and the particle is flying. Okay, right. It's gonna go straight direction right here. It's going to hit that wall. All right. What do you think happens? All right. In an ideal scene, this particle will just bounce off. Okay, and that's called elastic collision. So whenever a particle collides with something in an ideal gas, the particle just bounces off. Okay, without any loss of kinetic energy. All right, so there is no kinetic energy lost, okay, during that collision. So again, one more time, in ideal gases, when a particle hits a wall, it just bounces off, okay, and there is no loss of energy in that collision. All right. Now remember, guys, also gases spread out. So how do we explain that? Well, remember, guys, gases are moving, and we can say that gases are in constant random motion. All right, so they are in constant random motion. Okay, therefore they spread out. So, for example, right now I'm in a corner of a room. If I pass gas right here, eventually that stench will move across the room until to the very end. So it's going to spread out. So basically, this is the reason why gases spread out. Okay. This is also the reason, for example, your mom is cooking hamburgers for dinner. You go through the door, you don't even see your mom, can't even see the hamburgers, and yet you know that you have hamburgers for dinner because you can actually smell it because the smell of hamburgers actually spread out to your house. Okay. All right. Another basic assumption, guys, that we make for ideal gases is that there are no force of attraction between gas particles. All right. What does that mean? If you, let's say you have gas particle A right there, and you got gas particle B moving in the opposite direction, and they hit one another, they're just gonna bounce off one another. There's gonna be, they're just gonna deflect from one another, right? So there's gonna be deflected off one another. So they're going to be bouncing off one another. That's basically what it is. Okay. They won't stick to one another, but they will just bounce off one another. Right. Finally, guys, in an ideal gas, the average kinetic energy of the particle depends on the temperature. That's why we say uh, the average kinetic energy of the particle depends on the addition or removal of heat. That's why when we say temperature, guys, temperature, the definition of temperature, this is the measure, okay, of the average kinetic energy. Measure of the average, okay, kinetic energy of particles. Okay. So basically, these are the postulates that you want to describe an ideal gas, and we call this, guys, the kinetic molecular theory. But in real life, guys, real gases are complicated. All right, they do not behave ideally. Some gases, when they bump into one another, they experience what you call an intermolecular attraction, or simply put, sometimes they react. Okay, real gases do have volumes. They have different sizes. They not all of them are like super tiny. There's like super tiny and slightly tiny, but the point is they have different sizes. Okay. Most of all, guys, when gas molecules hit the wall of a container, most of the time they're not elastic. Okay, they have loss of energy. Kinetic energy is transferred. Okay, so that's basically what gases are in real life. Okay, but when we do calculations and look at real life gases, or real gases, guys, it becomes very, very complicated when we do uh, simple calculations, right? So when we do simple calculations, guys, we actually imagine we're looking at ideal gases. All right. So again, for our next few calculations, for the next few things that we're going to discuss, we're actually going to be looking at ideal gases. All right. So let's use our imagination. Okay. So, guys, let's say, for example, I have a gas inside a balloon. Okay. And I ask you to describe that gas inside that balloon. How will you describe the gas inside the balloon? Well, you can describe it, guys, in terms of four variables, what you call the pressure of the gas, okay, the volume of the gas, which starting today we'll just call V, by the way. Pressure we'll call P, okay? We can also describe the temperature of the gas, which starting today we'll call T. And remember this forevermore. This has to be in kelvins. Okay. And then finally, guys, we can describe it in terms of the amount of gas, which is usually measured in moles. And starting today, the symbol for that will be letter N. Okay. So, again, guys, when we describe any gas starting today, we're going to describe it in terms of its pressure, its volume, its temperature, and the amount of gas inside. Okay, guys, what is pressure? Pressure, guys, is the force per unit area exerted by a particle when it collides with the wall of the container. All right. So this, guys, is because of collisions, okay, of particles, okay, with the wall of the container. So again, this is because of the collision. So again, pressure, guys, is the force exerted per unit area because of the collision of particles with the wall of the container. All right. Now, how would you know if you're looking at a number that you're looking at pressure? Well, there are several units for pressure. It either is going to be in ATMs or atmospheres. Okay. It can either be in kilopascals or kPa, or it's going to be in millimeter mercury or mmHg. Okay, so those are the units for pressure. Okay, all right. Volume, you already know what volume is. Volume is the amount of space occupied by any type of matter. All right. So, how will you know if you're looking at a number that is volume? So, the volume, the unit for volume, guys, will be in either liters, which is L, right? Or milliliters. Okay. Temperature, guys, has to be in kelvins. All right. Let me say we said that. That's going to be the unit of temperature. Okay. You're going to say, oh, Mr. Chu, I don't know what kelvins is. I know what degrees Celsius is, and I know what Fahrenheit is. Okay. So how do you turn Celsius? Let's just focus on Celsius for now. How do you turn Celsius into kelvins? Okay. It's easy. To turn Celsius into kelvins, guys, you just add 273.15 to your Celsius. Okay, so for example, I have 30 degrees Celsius. What will this be in Kelvin? So you just add 273 to it, 0.15, and this is going to be 303.15 K. See it? How about, for example, we have, guys, 50 degrees Celsius. Okay, 50 degrees Celsius, again, you just add 273.15 to it, it comes to 323.15 kelvins. All right. What if we have 0 degrees Celsius? Again, it's the same process. Just add 273.15 to it, and this is now 273.15 K. Okay. And you need to remember this, the 0. Okay. 0 degrees Celsius or 273.15 K is called the standard temperature. Okay. Remember this. This is again, guys, called the standard temperature. And we use this for a lot of things. Finally, we just discussed this before, the amount of gas in moles. So if you say 5 moles, that's basically what it is. All right. So again, when you describe a gas, you describe it in terms of its 4 variables: pressure, volume, temperature, and amount of gas. All right. Wait a minute. Okay. So, wait a minute. Okay. All right. So remember, guys, we said earlier 0 degrees Celsius or 273 is called the standard. Okay. This is called the standard temperature. How about pressure? Is there a standard pressure? Yes, there is. It's 1 atmosphere. Okay. Or equivalent to 101.3 kilopascals or 760 mmHg. Okay. Together, guys, this condition is called STP, or simply called the standard temperature and pressure. So if you ever see this in your word problems, don't forget STP, standard temperature and pressure. The temperature there is 0 degrees Celsius and the pressure there is 1 atm. Don't forget. Remember, temperature has to be in kelvins. All right? Cool. Okay. So guys, we have 4 variables: pressure, volume, temperature, and amount of gas. Okay. Let's focus on the first 3. Okay. Let's focus on the first 3. Okay. So let's write that down. So we need to look at pressure, volume, and temperature. Let's find out the relationship between these 3 variables. All right. Let's start with pressure and volume. All right. At this point, I should show you a video that shows how things act inside a vacuum. So I'm about to show you a video that shows a balloon inside a bell jar where we decrease the pressure inside. Okay, we decrease the pressure inside the bell jar, and what happens to the balloon? The balloon expands. Right. Okay. So what happens here is, as you decrease the pressure inside the bell jar, the volume of the balloon expands. So as pressure goes down, the volume goes up. Okay. Right. Let's reverse this. Okay. If we put air back into the bell jar, the pressure goes up. What happens to the volume of the balloon? The volume goes down. Okay. See that? So if you look closely here, guys, the pressure is inversely proportional. Okay, to V. So guys, when we say pressure is inversely proportional to V, if P goes up, volume goes down. So it's like a seesaw effect. So it's like a seesaw effect. Pressure is down, volume goes up. Volume goes down, pressure goes up. Okay, so don't forget that's the relationship between P and V. All right, let's look at the next two variables. What's the relationship between V and T? V and T. At this point, I'm about to show you a video. I'm supposed to show you a video uh, that shows a balloon attached to a flask. Okay, if you heat up the flask, okay, the gas inside gets heated up. Okay, so as we increase the temperature of the gas, the volume of the balloon goes up. Okay, so increase in temperature, increase in volume. Now, if we let that balloon cool down, decrease the temperature, you're going to notice that the volume also goes down. You see it? So if you look closely at this relationship, we can say that V is directly, okay, it's directly proportional, okay, to T. So again, if V goes up, T goes up. T goes down, V goes down. Okay? So it's like an elevator. They go in the same direction. Okay? All right. So don't forget, pressure and volume, P goes down, volume goes up. Okay? Volume and temperature, T goes up, volume goes up. So let's look at our last relationship. It's between pressure and temperature. Okay. For this one, I'm supposed to show you the can crush experiment. Okay, where I heat up a can, all right, with a empty soda can, right, and then all of a sudden I flip it over on top of cold water. What happens there, guys, is I lower the temperature really fast and cover up the whole. Okay, the whole of the can, which means I'm lowering the temperature of the particles inside the can, okay, causing them to slow down so much. Okay, remember this. Uh, as your temperature goes up, the kinetic energy of particles also go up, which means the particles are moving faster, increase in motion, and you also have increase in collisions. Okay, the opposite is also true. So if we lower the temperature, you get a lower kinetic energy. Kinetic energy goes down. Motion starts to slow down, which means the particles slowing down, and you got less collisions, okay, on the wall of the container. All right. So let's go back. So in that can crush experiment, as T goes down, the volume suddenly goes down. It collapses the can because the can can't hold the 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 I mean pressure goes down. The pressure goes down, and the can collapses on itself because it can't resist the decrease in pressure. Right. It's also the same thing, guys, that will happen if I throw an empty can, empty spray can in fire. Increase in temperature will result in an increase in pressure inside the can. Eventually, guys, the can will explode because it can't hold the pressure anymore. All right. See that? So, given those three relationships, guys, given those three relationships, and let's write that down again. Again, relationship between pressure and volume, increase in pressure, decrease in volume. Okay. They're opposites. Increase in volume, you get an increase in temperature, directly proportional. And then a increase in temperature results in an increase in pressure. Okay, right there. So let's put this in equation form. All right, if we put this all together, all right, it forms this equation right here. Okay, this is called the combined gas law. This is P1 multiplied by V1 divided by T1 is equals to P2 multiplied by V2 divided by T2. Okay, so this is called the combined gas law because we just combined all three variables together, okay, to look at the relationship between pressure, volume, and temperature. Right. So this is our equation right here. So let's try solving using this equation, right? Let's just jump into the equation itself. For example, a 5-liter sample of gas has a pressure of 1 atm and a pressure of 100 K. What is the volume of the gas if the pressure was increased to 2 atmosphere and the pressure increased to 200 K? All right, let's figure this out. So we need to figure out givens. All right, so how do you do this table right here? This box right here would be where P and 1 intersect. So this is where you put your P1. Okay. Box below it is where you put your V1. This would be where you put your T1. Here, this is where you put your P2. This is where you put your V2. And this is where you put your T2. Okay? All right. So let's figure out stuff. The givens are the numbers in the problem. So let's figure it out. 5 liters is our first number. What is that? If you look at the unit, you're going to notice that this is volume. Okay. So you just need to decide whether this is V1 or V2. Let's just say you said this is V1, 5 liters. All right. Of a gas that has a pressure of 1 atm. Okay, it's fairly obvious this is pressure because it clearly says there that's our pressure. This is 1 atm. Okay. And a temperature of 100 K. See it? Okay, that's going to be our T. All right, 100 K. And this is good because the only temperature that we can use is in kelvins. All right. Now, remember what I said? The V, 5 liters is V1. Now, if you say 5 liters is V2, you must call 1 ATM as P2 and 100K as T2. Okay. Although that is actually wrong, it's still going to give you the correct answer, right? Again, if you call V 5 liters as V1, okay, you have to call the rest as P1 and P2. By the way, what does 1 mean? Okay, what does 1 mean? 1, guys, means initial. So P1 is initial pressure, V1 is your initial volume, T1 is your initial temperature, and then P2 is after the change. So this is your final pressure, volume 2 is your final volume, and T2 is your final temperature. So again, guys, when you say 1, this is initial. And when you say 2, this is final. Okay? All right, let's keep on reading. What is the volume of the gas? What is the volume of the gas? What does that mean? It means that you're looking for V2. Okay, right. If the pressure was increased to 2 atmospheres, so 2 atm is our pressure. All right. And the temperature increased to 200 K. So there's 200 K right here. See it? That's your givens right there. All right. So we have to look back again at our equation. What was that equation again? Our equation again, guys, is P1 V1 over T1 equals to P2 B2 over T2. All right. There are two ways of doing this. You can either solve first for V2 and find the correct equation, or you can go straight out and substitute into the equation and then figure out what's the final answer. All right. For this video, guys, I'm not gonna put in the units in the main solution. I'm not. Okay. I'm not gonna put in the units in the main solution, but you can do that on your own. I'm gonna put that later on. Okay. So Okay, I just want to focus first on if you know how to substitute or not. Okay, all right, here we go. So P1 is 1. So I'm going to change that P1 to 1. Substitute 1. Multiplied by V1 is 5 over T1, which is 100, equals to P2 is 2. V2 is X over T2 is 200. Okay, all right. Guys, I can do this without the units since as long as your two variables, the 1 and the 2, are the same unit, you should be good. Look, ATM is ATM P1, ATM is P2, so we're good. Okay, temperature, T1 is K, T2 is K, so we're both good. All right, how about V1? V1 is L, but V2 is missing. All right, let me tell you now, the unit has to be the same. So our final unit for V2 will be L. Okay, so there's going to be L right there. Okay, all right, let's go back to our math. So you can now do the math. 1 times 5 gives me 5 over 100 equals to 2 times x is 2x over 200. Okay, all right. Now we need to solve for x. Okay, we need to solve for x. How do you do that? You cross multiply these two. Okay, and what do you get? 5 times 200 is 1,000 equals to 100 times 2 is 200x. All right, I cross multiplied and that's what I got. So how do you solve for x? To solve for x, I need to divide both sides by 200. All right, 1,000 divided by 200 is 5. So x is equals to 5. And the unit again is L, liters. Okay, and that's the final answer. So if you notice, guys, the volume didn't change. Okay, the volume did not change in this problem right here. It kept constant. Okay, the volume kept the same. If two variables, okay, V1 and V2, P1 and P2, T1 and T2, if that variable does not change, that means that is constant. So again, a variable that doesn't change, so no change, is equals to constant, and we can actually take it out of the problem. So again, if the variable does not change, that means it's constant. We can actually take it out of the problem. Okay, what do you mean by that? Let's try another example. Ready? Let's saw this next example that we have. Okay, a 5-liter sample of gas has a pressure of 1 atm. What is the final volume of the gas if the pressure would increase to 2 atmospheres? So we can go do this really fast. We know that 5 liters is your V1, so P V1 is 5 liters. Okay, pressure of 1 atm, P1 is equals to 1 atm. All right. What is the final volume of the gas? So V2 is equals to X. P2 is equals to 2 atms. All right. What did you notice in this problem? In this problem, guys, temperature was not even mentioned. Okay. So if it's not mentioned in the problem, we can assume that the temperature did not change. Okay. Remember, because a 1 and a 2, right? P1, P2, that means there's a change there. So, does that mean that temperature is not really a variable here? No, it is. The problem is it's constant. Okay. If there is no mention of the variable in the problem, we can assume that that variable is constant. All right. So let's look back again at our combined gas law equation. It's P1 multiplied by V1 over T1 equals to P2 multiplied by V2 over T2. Okay. All right. If you look closely, guys, at our given, the temperature is constant, which means we can actually take it out of our equation. So we can take this out. See it? Oop. And we're left with this equation. You see it? It's combined gas law without the T. And why is that? Because our constant here is pressure. Oh, is temperature. And what's changing here, again, guys, constant, by the way, is not changing, right? And what is changing here is pressure and volume. Okay. You see this equation, guys? This is called Boyle's law. So in Boyle's law, guys, the temperature is constant, and what is changing is pressure and volume. So again, in Boyle's law, the pressure is, oh, I'm sorry. In Boyle's law, the temperature is constant, and what's changing is pressure and volume. Don't forget that. Again, Boyle's law, constant is temperature, changing is pressure and volume. All right. So let's plug in our numbers into our modified equation. Again, I'm not going to put in the units, but please make sure you do put in your units when you do the solving part here. Okay, P1 is 1 multiplied by V1, which is 5, equals to P2 is 2 multiplied by our volume, which is X. Volume 2 is X. Right. Now I can solve it. 1 times 5 is equals to 5. 2 times X is equals to 2X. To solve for X, you divide both sides by 2. And then X is equals to 2.5. And what is the unit? We have to look back at our chart. V2 is the same as V1. And this is going to be L, liters. You see it? All right. Okay. Let's try another problem. Okay. Let's try another problem. But before that, again, let's summarize. Boyle's law is when temperature is constant and what's changing is pressure and volume. All right. Let's solve this problem right here. And let's try to do this faster. So a 5-liter sample of gas, again, that's going to be V1, okay, has a temperature of 50 C. Okay, temperature 50 C. We can't use C, so therefore I have to change it to kelvins. How? I need to add 273.15. Okay, and what do I get? I get 323.15. Okay, so that's going to be my T1, 323.15. All right. What is the final volume? So this time we're looking for V2 again. If the temperature is decreased to 25 C, again, I can't use C. You have to change it to K by adding 273.15. And this is 298.15. So T2 is equals to 298.15. Okay. All right. Okay. What do you notice? All right. If you've been paying attention, you read this thing, there is no mention of pressure. Right. Does that mean that there is no pressure? What does that mean again? It means that it's what? It is constant. So again, for this one, temperature is constant, which means again, it's not changing. If it's not changing, it's not worth mentioning within the problem. All right. So let's look back again at our original equation, the combined gas law. P1 V1 over T1 equals to P2 V2 over T2. All right. Guys, if you look closely at our equation, P is constant. Therefore, we can take it out of that equation. Let's take it out. Let's take it out. And there you go. That is your new equation right there without the P. Right. What do you call this law? This is called Charles' law. Okay. And in Charles' law, what is constant? Constant is P. Okay. And what is changing here, guys, is volume and temperature. So again, what's constant here is P. Okay. All right. So how do we do this? Let's just plug it in. V1 again is 5 over T1 is 323.15 equals to V2 is X over 298.15. Okay. All right. So how do you solve for X here? If you've been doing algebra 1, you should know that if you have a denominator, okay, when solving for X, you have to cross multiply first to get rid of the denominator. So this becomes actually 5 times 298.15 equals to X times 323.15. Okay, you do the math. I need a calculator. That's what it is. Calculator. Let's get a calculator. So 5 times 298.15. 5 times 298.15 is 1,490. So I'm going to put it right here because I don't have a lot of space. This is 1,490.75 equals to, and what is 323x? 323.15x. All right. How do you solve for x? Divide both sides by 323.15. X is equals to what? Okay, our x is equals to 4.61. Or let's just say 4.6. And again, the unit will be the same as the other variable, which is liters. There you go. So again, guys, this is Charles' law now, okay, from our original equation from combined gas. Here, the constant here is P. All right. Okay, let's do one more. Now, what if, okay, what if, read this problem right here, and let's do this really quickly. A sample of gas has a temperature of 50. Again, you have to convert that to K, and that's going to be our T1 plus 273 is 323.15. Okay. And a pressure of 1 atm. So there's 1 atm. Oh, P1 is equals to 1 atm. What is the final pressure? So P2 is missing. If the pressure of the gas is 25 degrees Celsius, again, we can't use 25. We can't use that. All right. We can't use that. Therefore, I add 273.15 and this 298.15. All right. So again, what do you notice? There is this time, guys. There's no V. Okay, we're missing our volume this time. Again, doesn't mean that it's not there or it doesn't have volume. It simply means that the volume here is constant, unchanging. Okay. All right. So let's look at our original equation. Our original equation is P1 V1 over T1 equals to P2 V2 over T2. Hey, this time the V is constant, therefore we can take out the V on both sides, take out the V on both sides, and this is what's left behind. P1 over T1 equals to P2 over T2. This is called Gay-Lussac's law. Gay-Lussac's law. Okay. And what is constant here is what? V. And what's changing here is pressure and temperature. All right, pressure and temperature right there. Okay, so let's go substitute this. Let me erase this really quickly. And let's go straight substitute into the equation. Okay, what is P1? P1 is simply 1 over 323.15. P2 is X, so X over 298.15. Again, guys, if you have a denominator like this, don't forget to cross multiply and you get 298. Whoop, let me clean that up a bit first. 298.15, okay, equals to 323.15 x. Okay, and how do you solve for x for this one? To solve for x for this one, I just divide both sides by 323.15. So I'm going to divide this by 323.15. And therefore x is equals to what? 0.9. Let's just round it off there. And again, what's the unit? Just look at the other one that's there. We're looking for P2. Therefore, I have to look at P1, and this is ATM. So we're going to call this as ATM. All right. There you go. And again, this one is Gay-Lussac's law. All right. So let's put all our problems to the test. Okay, let's put all our knowledge to the test. And let's see if we can figure this out. For example, you have a pressure of 1 in 490. Okay, temperature of 22 degrees Celsius. T2 is negative 24 Celsius. We're looking for P2. Okay, let's put them in the boxes. So again, guys, temperature you have to convert to kelvins by adding 273.15 or just round it off to 273 and you get 295. Okay, the same with the other temperature, negative 24. I have to convert it to kelvins, so add 273 to it and this gives you 249. Be careful of the signs. Okay, again, temperature we have to make sure that it has to be in kelvins. All right. So what are we looking for this? We're looking for P2. Okay. All right. Most of the time, guys, if you notice, I use X, but for this one right here, I actually put in the question mark with the appropriate unit. And again, how do I know what's the unit? Just look across. Okay. It should have the same exact unit. All right. So what do you notice about this? There is no volume. All right. Hey, for this one, X, instead of just crossing it out like this, guys, they put in X. All right, so be careful of this. Okay, for the other problems here, guys, the unknown is the question mark. The X is simply not there. All right, and again, when you say it's not there, it simply means it's constant. Okay, they are constant. All right, so how do you solve this? So let's plug it up into this equation right here. There's no V, so therefore I can take out the V. Okay, you can take out the V because there is no V. Okay, take out the V. And then if you want, you can either isolate P2 or you can just simply plug it into the equation. All right. In this case, guys, we isolated P2. So how do you solve for P2? Okay, I multiply both sides by T1. All right. So, I multiply both sides by T2. And the T2 disappears. Okay. And what do I get? P2 is equals to P1 multiplied by T1 divided by P1 multiplied by T2 divided by T1. Substitute the numbers in. Okay. 490. T2 is 249 over 295. And then you get your final answer right there. Okay. And that's how you do your problems for this one. Please make sure, guys, that you actually look over the PowerPoint one more time before you do 17.1. All right. If you have any questions, contact me to the remind or email me, and get ready for our next time we see each other. Right.